Hello again. This is Claudio from FEA.com. Short reminder about our website with lots of simulations, books, tutorials, and everything you need to support your simulation needs. So the topic for today, let me share my screen. I was mentioning about FEA.com, where you can find simulations, books, tutorials, and so on. The main topic for today is simulating a spine assembly with cartilage, and maybe we will also insert an implant if we have enough time. So let's firstly go on GrabCAD and see what we have at our disposal, and show you that in 9 cases out of 10, the geometry is not usable and is not useful. Yes, right now only this can somehow be used with editing, of course. I'll open it, and also I'll open some other 3D models for you to see how reliable they are, meaning that they are not so reliable being in general being fused together. They are merged assembly. Oh, this looks nice from the outside. I'm going to open also some implants which keep or replace the cartilage between the vertebrae, and yes, let's see what else we can produce here. This is only two. There are only 2 parts here. This is only 1 part. I'm interested in having at least 2 or 3 vertebrae. So this is what I think we will use in the end. But let's go and download some of these scenarios. You know what? Let's not waste time. Maybe open it, and I'll prove to you that is not an assembly. Let's see if is there any message. So until now, no message. We like silence. Look here what we have. These small spikes will complicate the FEA, and these vertebrae, they are clearly fused and merged together. So this is useless, we can say. Spine left 2 STL. This looks promising. And it's kind of promising. Is it cut or am I? Ah, no. It's fused. Look here, the vertebrae. They are fused. So, not useful. This is a step, but it's the pedicle screw whatever system. We want the entire assembly. Come on. This looks promising, and I think we should use this, and this would mean that we will avoid additional modeling work, and we know how tedious is when importing and converting STL or OBJ shell files into solid geometries. I will download this. It's called L4, L5, so lumbar vertebrae 4 and 5. Lumbar segment. This is interesting. Let me download this because I would like to simulate a simple, clear biological real spine, and also I would like to replace the cartilage with such an implant. For example, what have we here? A bigger assembly. Do we have a bigger assembly? This is bigger. Hernia STL. Is it fused? Yeah. Yeah, it's clearly fused. Look here. So it's only one part. Exactly how they got it out from scanning, how they obtained it from scanning. This looks so very nice. Do we have an assembly? We have an assembly. Let's download it. Of course, I have used almost all the geometries. I have tested and opened and edited and tried to convert. And some of them I kept them in my mind, also in my on my computer. View all. We have more implants here? Let's go for the most basic ones, and I don't know, maybe they are STL. If they are STL, they are kind of useless. Oh, solid part. This is useful. Already solidified, or yes, STL. This will impose lots of work. These ridges, lots of work. No, I don't want. STL. These peaks, due to knurling or whatever operation is this, lots of work. No, we're on the basic. We're on the basic, let's say, stage, and we want to attract beginners. Hence, I want to use the most quickest to use models, and we want to jump pretty quickly into meshing and FEA. I also saw this skeleton. Let's download it. They look very nice. Let's hope they are very nice. Come on, is it downloaded? Yes. Spine fixator. What is this? Spine fixator. Sincerely, I don't want the fixator. I want the spine. Spine. What? Fixator. Ambulance, I don't care. Where is the body? I have a spine here. Come on, don't tell me I need to hide everything. You know what? Human man. Ooh, yes. Oh, yes. This looks nice. This looks very nice. Let's open. This is a step. Yes. I liked it. So I'll go for this spine fixator, and maybe let's open it. The spine fixator. Let's open the spine fixator. Space claim. I open space claim. Open again. Spine fixator. Where is spine fixator here? S. Instead of CDoc, let's go for step. Spine fixator. I have lots of hopes for this. So this means, remember, if we can find a very well modeled 3D model, then remember that you can also download it and use it from GrabCAD. Until it opens, let me show you an alternate way that I use very often, meaning that I'm going for such, let's say, artistic websites. Yes, it's, yeah, in 99.9% is not CAD. These are models that are for sale. They are made using Blender, Cinema 4D, 3D Studio Max, Maya, ZBrush. So, and it's guaranteed that you will find very nice models for a price. Nobody forces you to go for 400 or 100, maybe for, 22, 19, for example, $19. And you can see the geometries here. It's nothing step or parasolid, but with some effort, with some persistence, you can convert them in 3D model, all right? So this is one option, and this option is almost, how do you say, exhaustive. I want to say that you can find anything and everything here. So let's keep this in mind, okay? And don't be afraid to spend some. For example, yeah, this model lacks the. No, it has the discs. Only they are somehow. Why did they feel the need to separate them? I don't know, maybe for visualization purposes. So keep this in mind, yes? Also, my other alternative is Turbo Squid. And if you search here, spine, from very complex models to the simple ones, of course, you have filters, yes? Lowest prices, go and feel free to use whatever you need more. This spine that 84% completion. Yeah, why not? Meanwhile, let's open another space claim and insert other geometries. Do we have any message from the audience? No. All right. Come on, space claim, open. I'm wondering at this percentage if it stopped, if it froze. We will see. With some patience, we will see. So space claim opened. Let's open other models. What have we here? Let's go for all files. Spine fixator is opening now. Let's go for this is the implant L5 plus L4. Why not? It looks very nice. Also with this cartilage here. Oh, yes, it looks so nice. Do we have multiple? Oh, we have multiple discs. Oh, this is very nice. Let's see what opened here. This. Sincerely, I don't care about these parts at this moment. Why I only care about this? So it lacks the cartilages that you can see in the other model. You see these teal or turquoise, I don't know what it's called, the color, almost blue, yeah, these cartilages. So because that model is almost too complex for me. Just remember it, yes? You can find it on GrabCAD, L5 plus L4. I'm more inclined to use this model because it doesn't have so many parts. I will only isolate 2 or 3 vertebrae. At this moment, let's also open another. I wanted to open this L4, L5 fixation by stem. The spine assembly is very complex. Let me show you how many extra parts it has. Yeah, but they don't show. Comments, yeah. Maybe something like this. Look here. So it has these intertransverse ligaments here, yeah, on protrusions, let's say, also here, anterior longitudinal ligament, supraspinous, interspinous ligament. What I would like to draw your attention to is how complex is this model is in reality. Look here. Yeah, these small protrusions, spines, or how they are called spinous process. This is supraspinous ligament, anterior ligament. So these parts, all the parts, they don't just float in the air. Yes, they are carefully. These parts here, they are carefully united and held together by ligaments. Yes, you can see here, for example. Look here, ligaments between each portion in order to ensure that it holds the assembly together. Yes, look at this is a complete assembly of the spine. Yes, we're using a basic model and simplified model. I opened L4, L5. There are some things here which, sincerely, I don't want to touch, I think. Because it has these screws, the screws are pretty complex with these cavities inside. So if you persist and insist, you can find nice models on GrabCAD. Let me close this because it adds many parts. These are extra parts. So I don't want to complicate the model because the focus for today should be FEA and less modeling. So here, let's stick with some of these. For example, right-click, locate in structure tree, and I will right-click, delete. We are pressing with. I will press on the bone. And yes, let's use more. Something like this. Right-click, locate in structure tree, and delete. I lost the selection. All right, and here, triple click, delete. I would like one of them to replace it with an implant. We'll fixate one side and we'll compress the other side, yes? Now, let's insert Let's insert some implants. Spine implant cage. Let's see how it looks like. Oh, STL, no, because it's a lot of work and we don't feel like working too much at this moment. Spine fixator. Okay, we opened some cage, so this cage is not usable. Can I use this? I think I closed some downloads too quickly. Let's see if this opens. What do you know? It opens something. Yeah, we can see the flexible part. Yes, it is flexible here. And yeah, let's see this thing. Do we have like something like zoom extents? Yes, here. Then where is this? This part. Where is this part? Can we see it? Yes, it's here. Let's move it here. Also here, yes. Let's scale it with 0.4. I would suggest this is an assembly, yes? No, it's a solid. I thought it's an assembly. All right. You know, so much for the flexibility. I wanted these to be flexible, but this part blocks the flexibility. Yes, it doesn't allow for the bending of the two sides. So, all right. Let's see how this is inserted into spine. It's called spine fixator operation. Spine fixator fixations. Spine fixation. Yes, my question is if yes, we can see here some implants here. This is what I would like to do. I would like to here. No, this is with screws. Can I see this in a better? Yes. Ooh, this looks nice. So according to me, this side should be on the interior side. Yeah. So this is the exterior. It's I think yeah, it's cervical. It's here, close to the neck. So a narrow side of the implant will be towards the exterior. What I would like to say is this side will be towards the exterior, yes? So, and this side, it serves for the centering and maybe fixate additionally with such screws or plate, yes? So just imagine if you have multiple implants like this, then you can come up with a screw for example, here, yes, you have a screw, and if you have an implant, maybe, as you can see here, yes, you can attach the screw on the main wire, like here, yes. This you can attach this screw to the main wire that goes and encompasses more vertebrae. So I promised to scale this part, pick an anchor point to scale the body from. We don't care at this moment exactly about the anchor point. 0.5, let's make it half. Perfect. I think we will need to make it even more. Yes. Where should we put it? Let's put it above, because I see this disk is bigger than this disk. So triple click delete, and I will scale again, because it's not enough scale, it's too big. Let's scale it again, pick an anchor point, we don't care. Let's click the solid, and maybe, I don't know, 0.7. Yes, 0.8 again. Yes, and now let's just position. Maybe we need more scaling. Yes, let's assign more scale, or maybe dilate, displace these a little, just a little to accommodate what we have here. Oh, this looks now so nice. I would like for these ridges, yes, for this serration, to cut the bone. So this is why I would like to I'd like to have a bigger implant. Let's rotate, yes, something like this. And I would like for this screw not to touch here. Because we're not using it, we will just remove it, yes. Split body, this is the body, I'm using this face as a reference. Yes, we don't care about this. But sincerely, because I would have liked to see some compression, either I will modify this diameter, yeah, either I will remove the entire, this entire oval and or whatever shape is this. Let's see what will with pull what I can do. Do we have a dimension? We have 3 millimeters. What will happen when I pull with 6.53? 6? What's happening? Oh yes, this would mean that I can have some flexibility. I would like in the end to see the compression of the cartilage and the compression of this this implant, yes, and I would like it to be visible. 5.75. Yes, I'd like it to be visible. Perfect. Let's keep this. Show wall. I don't know how much compression we will have, but let's see. Let's change the visibility transparent here in order to see how much we will cut. Yes, more here. Okay, more to the right. And here maybe 1 degree, maybe. Yes. So we have this will cut here, this will cut here. I remember about Prestige disc implant. I would like to see how big is compared to. It's pretty small compared to the original disc. So yeah, so it's normal to be a little smaller than the original disc, you know? Let's keep this. I would like to save it. Today is 28, I think, yes. And implant, yes. V1. Of course, as always, prepare interference. We have these. For better contact here, I would like to make this. Should I make this bigger or not? Let's hit here the green check and see if it removes properly. Hide others. So here it kept the serration, and I can see now that it's not properly oriented. I forgot to look like this. From this side, yeah, it's a beginner mistake. No worries. We will solve it right away. Can I right-click source internalize all? And this, I would like to name it implant. Here, right-click, delete empty components, because I would like to have this as the disk. Yeah. So this is thoracic, vertebra. This is another thoracic, T8, and this is the T7. All right. Let's drag and drop all of them. In order to have the optimal naming and ANSYS. You will see in a few minutes. Right-click, delete empty components. Let's drag and drop them here and delete this sub-assembly. Save. Everything is very clear now. I would have liked to have more touching here. Let's scale this just a little, 0.1 maybe. 1.1 in the end, and you can see now. Let's move it a little to the left. But we have a very big should we care or should we not? Let's have it like this. Maybe move it towards left a little. I would like in the end to have more touching faces here, because there will be touching faces here on the right, and there were less touching faces on the left. Look here, prepare interference. Oh, yes. Now I have proper touching faces. Maybe let's move this a little to the right. Design, move, and how big is a little? 0.4 maybe. Prepare interference. Yeah, we're going there. Move 0.25. Prepare interference. And yes, we encompass more edges. Let's say. Let's leave it like this, okay? Right-click source internalize all, and this, let's name it as version 2 in order to have a nice backup. This concludes our modeling session. Let's make a small section view. Look here. Scale the disk, yes, to avoid such gaps. We have a nice touching here. So yes, we're satisfied with what we have. Save, close. Because I have a similar simulations made with static, let's go for explicit dynamics this time. Do we have any message from the audience? There is one message. Hello, sir, where is the snow? Results I paid for, but you didn't upload the video. Results, but yes, maybe you paid, but you paid for simulation. There is no video, so in the future, ask for a video or see if there is a video. For example, you are going for, let me give an example. Expert FEA snow, yes? Let's say this one, yes? So when you are going on the solved FEA, you have this, and it says, get the ANSYS make file and 3D model. Nobody says anything about video. Here says, click for video with results. Yeah, there is no tutorial video. So before purchasing something, open your eyes, enlarge, increase your attention very much. Or you can give me an email and ask, hey, is there any video tutorial? And you'll get a quick reply, no problem. So we were here. Let's open version 2. I would like to have this in my work folder, which is this one. Import geometry browse. Look here, all right. Let me copy the name because I would like to have it here. Save as. This is trim 12. Yes. Regarding the materials, I remember having a bone nonlinear, and for the cartilage, I will create a cartilage. Let's see some mechanical properties. Spine cartilage mechanical properties. I'm looking for Young's modulus, Poisson ratio, something like this. Compressive modulus, no. Oh, here. We have a Young's modulus here. Okay. I'm sorry if you don't see it very well. I also don't see it very well, if it helps. What is this? Relaxation modulus. No, no, no. Cortical and facet cartilage. Ooh. And we have, oh, look here. Ligaments. This is very nice. So 0.01 gigapascals. 0.01. Do we have a Poisson ratio? We have, yes, 0.3. Are you sure? So high? So high, I mean so low. Because it should be close to 0.5, 0.4. You know what? I will make it 0.45 because this is what my common sense says. I don't care about this. Density. Do we have a density? Spine cartilage density. It should be around 1000 or something. Zero point 0.5 gram per. Is this cubic centimeter? No, it's on surface. It's like a surface density, let's say. All right, you know what? Let's convert this in what we know. 155 kilograms per cubic meter. Yeah, why not? 155. This is cartilage, and we have a titanium. Let's make it nonlinear. Titanium alloy nonlinear. All right, we have the bone defined as also nonlinear with bilinear isotropic hardening. Titanium again with bilinear isotropic. This cartilage is defined linearly, but let's hope it will not give too much, too high values, let's say. Do we have any question from the audience? No more questions. All right. Remember to do whatever you can, yes, including the use of AI, because it's a very powerful tool if you know how to use it, all right? So this looks nice. Let's go. We have the kind of the proper naming. Disc as a material property. What? It's already cartilage? Yeah, because now the default became cartilage because I deleted the structure still. These are the bones which will receive as a material nonlinear bone and the implant in titanium. Connections. I don't really care about the connection here. What I would like to do is I will keep the default frictionless and let's assign manually. For example, body interaction. There will be a bonded body interaction between, let's assign like a pinball radius, yes? What distance should we have? 3 millimeters? 5 millimeters maybe, you know what? 3.5 millimeters in order to find, you know, nodes from this side will find nodes from this side. This is why I kind of wanted something in this range, you know, to have like the diameter of the circle that you see here. And I would like to act like a pinball radius. So, and here Control B to select solid bodies, only these two parts. This is one pair. Right click, duplicate, and we will select these two parts. Apply. Duplicate, we will select these two parts. Apply. Duplicate, we will select the remaining two parts, these two. This is all. And I have the default frictionless in case that these portions will touch. Yes. Let's see how exactly the naming of those spines. 5. They are apophysis. Apophysis. Okay. All right. So yeah. Facets and apophysis. All right. In case that these two apophyses they touch, we'll have the frictionless contact. Let's make here quality. I would like low. Save. Right-click, generate mesh. Yes, it looks like this, and I like it. Can we make it? Yeah, the default is 8 millimeters. Let's make it, I don't know, 7. Or even 6. $16,000 nodes. All right, let's make the section view. Here. So I think there are some gaps here, but I assigned an offset in the body interaction, if you remember. Yes, and you know what? Let's make it 5. $24,000 nodes. Let's go with this. See what gives, what results we shall have. All right. So end time. How much should it be? Let's start with small value. Here, let's make inertia of 0 due to no, and here 100 result number of points. Some loads. As I promised, I would like to fix these faces. Let's change the selection mode for faces. Does it work? Why should it work? Why should it work? All right, let's go for single select then. Control F. This will be fixed. Environment fixed. And here I would like to apply pressure, because we kind of know the load, yes? So the load, let's apply a force, yes, which will become a pressure. The force is maybe half of the mass. So for 80 kilograms, 40 kilograms, or 30, 35 kilograms. All right, so downwards, yes, so minus z-axis, minus 350 newtons to account for 35 kilograms. It's pretty high up, yes, so it's not half of the bar, yes, so it's not 500 newtons, it's less. So let's press and see what will result. Yes, deformation, stress and strain. Switch to automatic mode. In here, deformation again, strain and stress. Do we have energy? No, but I would like to see the first reaction here in the fixed support. And we'll look on some pressures a little later. So at this moment, we cannot access extra results. After we have solving, after we have results, we can access this bottom worksheet, and it will come up with additional results, many more results, yes. So solve, let's have a feeling about the duration of the solving. Clear generated data, solve. So how long it will take? 1.7 hours. All right. And it kind of stopped. For fun, let's see what is this element, to whom it belongs. Right-click, select mesh by ID, elements, paste, create name selection. Let's see to whom it belongs. It belongs to Yeah, it's a good question. Move the section plane. I don't know if it belongs to the bone or to the implant. I think it belongs to the bone because the bone is more problematic. Compressible. So let's move this. Something like this. It belongs to the bone. Yes, clearly it belongs to the bone. And let's move just a smidge here. So yeah, clearly it belongs to the bone. So this means we might need to refine the mesh in this vertebrae, in this vertebra. All right. So let's just modify the mesh just a little. Overall, yeah. 5.5 or 4.5. Save, solve. Because it takes around 1.7 hours, let's make here maximum energy error 0 because we don't want any errors. Here, let's make it 1e minus 6, minimum Courant Friedrichs Levy time step. And here, I don't know, maybe 10 maximum part scaling to help decrease the solving time. Save. And solve. So we went 28,000 nodes. Yeah, we're so well. 10 minutes. It would be nice. Maybe it stabilizes around 15 minutes, and hopefully we get no errors. And yes, let's hope for the best. Now we are at the portion where we admire and try to learn what other colleagues have done in this field. All right. So ANSYS fine. This is we know this because I made this. Mr. Wan Muhammad. Let's see what has he done. 10 minutes. Structure steel. Young's modulus. Oh, yes, big value. But I hope he changes the name, I hope, because it's a little, I don't know, it's a little to keep structure steel. Please make it bone or cartilage or something, no? Don't leave it steel. He wants it steel, okay. It's his option. So he has a backbone STL. This means he will convert it. By the way, this is yes, you see, even though it's an assembly, it's a fused. The vertebrae, the disc, they're fused, and he does what, I think he does what a beginner does. He reduces triangles. Yeah, I agree with this. He is shrink wrapping. This is more than beginner. This is advanced. Yes, for a nicer resolution, and in the end, convert to solid. But it's a part. It's not an assembly. What we're showing today here, this is an assembly. Yeah. No facets, no. Yeah, smooth geometry. This is what we should aim for, to control everything in the mesh. So, nice beginning. Importing the material is default structure steel with better mechanical properties. This is static. I hope he makes here large deflection on. I hope. No, he left it off. He applies pressure. By the way, he is forced to live with this meshing. He cannot change the meshing. This mesh is dictated by these facets. In principle, you cannot. You are forced to mesh like this, in principle. But if you are watching our live stream, you know there are other ways to smooth, to obtain smoother surfaces. So he's fixing, applying a pressure, and he fixed the other side, I hope. Oh, only pressure, he forgot to fix. Come on, please fix, please. Yes. But one question. He changed, at least he changed, he rotated the geometry. Because yes, he rotated, all right. I'm skipping too much. So he fixed on one side and applied pressure on the other side. And some nice results, 0.2 microns, 2 microns displacement. All right, it's a part after all. It's a nice start. I hope he improved, Mr. Muhammad. Let's face the reality and see some intermediate results. It looks so nice. It's nice that this flexible side is on the exterior, because it will be bent something. It's flexible. And here is the rigid side of the implant. It looks very nice. For first simulation, for first trial, it looks very, very nice. Let's see some stress values. Uh, 5. Yes. You know, there should be different scoping. Look here. Solution information, result plot, stress. And here we should have different, for example, we should have different values. This is metallic, and we should not try to compare the stress in the metal with the stress in the other parts. So look here, this is more realistic. Yeah. And strain. Right click, adjust to visible, and the same. There is a difference between the philosophy of being metallic or non-metallic. What? It escapes here somehow. We don't care too much, let's say. All right. So this is abacus, space claim, facet, spine. But how do you work with what seems like a single part? Let's see. Oh, multiple parts. Shrink wrap, yes. Everyone goes for shrink wrap. Someone who knows about AutoScan. This is good news. Finally, we have something to learn. He has different parts. He knows AutoScan. Yes, he or she, they are on the right path. Femur, everyone goes for femur. This is our prestige LP disc simulation. I'm wondering if I should have had this flexible side here on this side, I'm wondering, but until now I didn't find. Spine disc implant. I didn't find the correct way, the correct orientation. This is rotating, but I would like to see without this rotation. Mhm. Oh my God, such complex work. So you see this opening is on the inside. In my implant, in the model that I use, there is not a clear opening, let's say. Mm-hmm. Yeah, you know what? Feel free to rotate, no problem. If you'll obtain our 3D model or do something similar, you can rotate this 180 degrees and assign this flexibility here. Now that I'm thinking, we need flexibility on the inside, yes? This is the body, the rib cage and the inside of the body, and we would need more flexibility. So yes, maybe a rotation is advisable. So feel free to rotate. Because here, for example, I would have wanted this flexibility to appear, you know. Let's let it solve, and I will rotate it and remake the FEA very quickly. Hopefully it will be a quick modification, hopefully. So look here. This is another story, it's closer to the hip. Here is on the cervical side. I think I'm asking too much from basic scenario. So we should stick to the basic. Look here. No, no, no. Yeah, so specialists, experts should know the best how it should be modeled and simulated. So you see, there is a bigger angle here, which translates also to a bigger angle here on the inside. Smaller angle here, bigger angle here. Smaller on the inside, bigger on the outside. So this means I think we should have this reversed in order to have a bigger angle on the inside. Yes, you see here, this is a bigger angle, this is the inside. Should reverse this to have here more flexibility, this flexible part, to have it here on the inside. Something like this to match. Let's make the match, you see? So this is the flexible side. It should be here on the inside. Let's see quickly if I can replace it. This is why I made a duplicate V geometry. We have here, let's animate. Scale is 1. Let's exaggerate just a little, not so much, not 18, let's make it 5 maybe. Yes. So look how elastic is the cartilage. And this is very rigid, let's say. Yeah. This is not very revealing because we have the peak in the cartilage which wants to get out, but is forced by the bonded direction. I will not stay on this. Here I'm interested. Yeah, with a force reaction here. It kind of interferes here because of the scale. Yeah. If the scale is 1, there is no interference because we have the frictionless body interaction. And the body interaction should act and oppose the interference there. So let's quickly modify and see if we can give results quickly. I will duplicate this. I will rename the geometry V3. Double click, and I will reverse the orientation of the implant. I think this is the close I have. Yes, I would like to have. Firstly, let's replace this if possible. Is it possible? Let's replace this with V1. I will copy paste it in my folder. I will edit it in Space Claim. Let me check my smartphone. All right. So this is V1. This is a version before the cutoff, before the combine operation. Remember to make new versions. Yes, keep before making the combine, this one, the prepare interference. Before solving this, make a new version. So let's rotate it with 180 degrees. Yes. Prepare interference. Yeah, let's leave it like this. Right-click source internalize all, and I said that I will save it as V3. Save as V3 here. Control S to save. Now interference. Let's solve the interference. Save. Double click. Any question from the audience? Yes. When we turn on mass scaling option, the solving time will be faster. Yes, but will the results similar without using? You can check. No problem. Usually the density is artificially increased in some elements. So feel free to check. When we should and should not use the mass scaling option. Just test it, because the advantage of using mass scaling is so big that it's, we would be fools not to use it. But feel free to check. Maybe on simple models first, and then with complicated models. From my experience, at least for the level that I'm working on with basic simulations for YouTube, it doesn't matter so much. So just test, you know, just test. So disc is cartilage, this is bone implant. Oh, it remained. We don't care about contacts. Do we have these? If they are kept, then I'm very pleasantly surprised. Yes, I am very pleasantly surprised. Mesh, generate mesh. So, nice software. ANSYS workbench, very user-friendly. What have we here? Let's see. The first thing that I would do is maybe go on virtuology here. Control B to select the solid model. Here, make it a medium. Right click, generate virtual cells on selected entities. So it kind of healed something. I want it to heal here. Yes, because there is a problem with this cutout, of course, yes. Let's see if now it generated the mesh. Virtual topology is a very good way to heal the geometry. Ah, what do you know? I was right. So 28,000 nodes as we had in the past. And let's make this, you know, a little finer sizing. 3.5. Maybe 3. I'm looking here at the number of nodes to see how much it gained. Yeah, let's leave it like this. Here, in order not to have so much right-click and name based on definition, in order not to have so much strain, let's make here even less. I don't know, maybe 2 millimeters, the offset. Also here, maybe 2 millimeters. Because if we have an expanded offset here, these nodes will artificially kind of touch or be glued, and this is why we have a very high strain. Yes, here and here. Keeping a smaller offset, maybe we'll have not so much strain. We don't care about much strain inside, but outside it's not realistic. It's not decent. It's not professional, all right? So let's solve it. Right-click, clear generated data, and solve. Again. We have some mass scaling here. Let's make it 25. Maximum par scaling. Yes. Save. Solve. Clear generated data, solve. 10 minutes. Yes, we should be fine. We were here. Shit, metal. This is a model FEA made. I found the model as one part, so they are fused together. But because the model is so nicely detailed, I still used it for a model FEA. It's not such a big deal. It's not something complex because it's. Oh, I should change this instead of assembly. Maybe I should make it one part. Supported. You know what? Let's write here geometry. Where is the spine? I was looking for spine. All right, let's go for vertebrae or vertebra. This is made in ANSYS Hall of Fame winner. What do you know? This is not made in Space Cream? It looks nice. It corrects the scoliosis with this wire. And the vertebrae are being centered, let's say, aligned with the wire. Yes. Yeah, nice work. But doing it in mechanical or APDL, I think it's not so cute. Does it work? Yes, it works. Oh. It perforates the vertebra. It perforates the spine. Yeah, it's nice. It's basic. It's rough around the edges, but it looks very nice. Yeah. I had to keep the solving time shorter. You know, this is why I used. This is why I usually use. A quartz mesh, yes. This is ANSYS, no? Yeah. This is. It's a compression or something. Yeah, nice work. (1000 megapascals). Yeah, so he clearly used linear materials. No hardening defined. Yes. Nice work, nevertheless. Yeah, and this is one of my most viewed simulations. My most viewed, it has close to 400,000 views. It's pretty old, 6 years. I think I should remake it and make it more decent. In my perspective now, this is a beginner work. But yeah, I can always remake it and optimize it. I would like to have cavity inside. I would like to have at least lungs, if not also heart. And yes, when I will remake it, I will make a cavity with lungs, heart, and it will be nicer. This was recommended by YouTube, and it brought me so many views. Only on this plane. So that plane is the medial or sagittal, how it's sagittal plane, okay? So this is the range of motions, the angles on the sagittal plane. I would have wanted to also see on other planes. Nice. Anatomy, yes. Yeah, this is I obtained this nice assembly, and I wanted to kind of test it. So I made this stroke test, let's say. And yeah, it's pretty nice. 1, 2 fingers kind of fly away. Yeah, it's a first trial, so. A client wanted to check to see if I can do such a draw test, because there was a, how do you say, work accident at his company, and they wanted to see such scenarios. So, Expert FEA, your top repository, your first and final destination for biomechanics simulations. This is some CFD. So many disclaimers and no more images. This was made 3 years ago. It looks nice. It can be optimized. There are lots of problems with the meshing. Meshing anatomy is not so easy. This is why so few people have decent models. They have a femur, one bone, and that's all on YouTube, but they don't have such detailed models and assemblies in biomechanics. Look here, yes. They are supposed to be bones here, and this is a knee joint. Yeah, I will not comment anymore. 3 minutes. Let's see how it behaves. it's so much nicer because the gradient is correct here. It's not a sudden jump of values. Yeah, it's so nice. So nice. Do we have the big values here? No, not so big. Look here how nicely they work. There is a maximum there, but we don't care too much. Yeah, it looks so nice. So nice. Any question from the audience? No new question. Here is like a stand, maybe? With what is this? What? With the wrong scale? What? He's not going for the result scale. And why do you publish something like this? Why? 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 What is the use of this? Why? Why? It's the first time when I see like a shoe. Yeah, nice. Here, a spine with a rib cage, yes. It was made 2 years ago. So hard to mesh it, so many errors and so problematic. So these are organs, by the way, these are organs, lungs and heart. So it was a lot of work to set it up and make it work. A lot of work, sleepless nights. You see internal organs, and it's yeah, it can be optimized after all. Everything can be optimized. Look at the lungs and the heart, yes. But yes, it's a nice work. Yes. So the FEA finished. I promised you that I will go here on the worksheet and show you additional results. I meant, let me show you some deformational vectors. Energy, compression, pressure. Pressure is here. Right-click, create user-defined results. Right-click, evaluate all results. We're approaching the finish of the live stream. So here we can click vectors and enlarge. Let's elongate a little these arrows. And let's increase the scale maybe 2 times, not too much. Yeah, something like this. Energy, right click, adjust to visible. Can I assign here, I don't know, 50 joules per kilogram? Or you know what, clear generated data. And I will select only these parts, the stiffer ones, in order to see nice gradients. All right, compress all. We also have section, just remember. This is a section view. Let's move it towards the center. Where is the center? Kind of this one, in the sagittal plane. The scale is 2, yes? And pressure, how much do we make this? 0.5? Just for fun, can I see only the implant? How it behaves? Yeah, the orientation of the force should be, I think it's more complex. But I see, yeah, this flexibility here. There is a flexibility. Look here. Like a bending, yeah, very small. These values are very small because, you know, it's a mechanical part and we should not stress it too much. Yeah, the highest strain is in the hyperelastic part. Ladies and gentlemen, this is the end of this live stream. Do I have something for the closing? No. Have a nice evening. Thank you for your attendance and good luck. Bye-bye.